All right, guys, and welcome back to Mr. Cole's class. We just started the last video. We started talking about electricity and magnetism, is what we were kind of getting into. And we went through and defined what a magnet is, and we looked at like different types of magnets like we're used to, and the cow magnet, of course, which I really love just because of the neatness. We talked about what it is to magnetize something because I don't know if you've ever done it, but like lay another piece of metal, like maybe a screwdriver or something, across a magnet, and you'll notice that object becomes magnetized. Now, it may not hold it, but all you're doing is imagining every little particle. And we'll look at like iron again. Imagine each single little particle of iron having its own tiny little north and south pole, and those could be oriented in many different directions. And so, in order to make a magnet, all you're doing is orienting all those particles essentially in the same direction. And then they kind of stay there. And what makes some things temporary magnets and some things permanent magnets is just their ability to maintain this orientation. Because natural over time, it's things tend to go back to this previously unmagnetized state that we look at over here. And we even looked at like mixtures, what magnets are made of. And predominantly iron is what we think of, but they use aluminum and nickel in there. And it's not that aluminum itself is you can't attract aluminum with, say, a magnet. So go home, try and grab a magnet, stick it to a Coke can. Nothing's going to happen. But we use these other mixtures in there with the iron to try and harden the iron or make an alloy that makes it harder for these particles to lose their magnetism, i.e. makes it harder for them to return to their previously unmagnetized orientations. So we discussed that in the last video. There was my pictures of my neodymium magnets, or neodymium. I am from Alabama. I'm sorry, my pronunciation is always terrible. What's cool about those is how strong they can be. You can get online, and for like $150, you can buy a 3-inch diameter neodymium magnet, which if we still possess video stores to this day, that would actually be strong enough to actually walk in and erase the tapes in the video stores. But anyway, that technology is gone. By the way, if you're wondering like about how did magnetism work in a VCR tape, well, literally the tape itself, like if you've seen one of these relics, they had 2 reels inside. And when I was a kid, I grew up watching movies on these things. Well, actually, when I was a kid, they didn't even exist to begin with. But they have a piece of tape, and the tape was black, and that's because it was a composite of iron that was inside there, and you literally stored data in the magnetic orientation of the particles inside there. So if you can imagine this analog data being stored and encoded in that piece of tape, and if you've got a strong magnet nearby, you would then effectively erase, reorient all the particles stored on that tape, and that would do it. So 8-track tapes, all those things were same line of thinking. And so we talked about ceramic magnets, which again is nothing but iron embedded in the material. And we kind of looked at these refrigerator magnets yesterday from that standpoint. And we looked at some uses. And I got confused yesterday on the maglev train. I was thinking that like 327, but turns out I found the video on YouTube. And let's see if I can actually pop that up. And there is that maglev train as it was seen on YouTube. And get ready. And they actually got that train up to 374 miles per hour. So incredibly fast train in Japan. So anyway, I thought that was kind of interesting. It's also interesting I can go to YouTube and just throw that video in my video. So anyway, continue on. But 374 is the top speed they've got it up to at this point. So I found that to be rather fascinating uses of magnetic fields. Let's see, we talked about magnetic fields themselves, the formulas, and my battery started dying right when we got to this concept of declination. But again, declination is nothing but the fact that if you remember yesterday, let's see if we can go back to that little thing I was doing yesterday. If I can get it sized back the way I want it. we were looking at the Earth yesterday. Ah, and this one doesn't have my Earth on here. This one just has the magnet on there. But if we remember, there's essentially, if we could have the Earth here, and let's see. You're probably going, Mr. Cole, what are you drawing? I've never been known for my supreme artwork. Wow, this could be, that's the worst South America ever recorded in history. Get some Aleutian Islands out here. But if you remember, essentially what we've got is in the Earth itself, you could imagine there being a bar magnet embedded in the Earth. And look at this. I'm putting south and north on there. We learned that yesterday. What we call the geographic North Pole, the geographic North Pole, is not actually a North Pole at all. But anyway, we still call it geographic north, but it's really our compass. The North Pole of your tiny compass is actually pointing at the Earth's South Pole. But anyway, we claim this to be north. But what's cool is geographic north and magnetic north are not in the same place. And so we talked about when you're using it for orienteering, it can be a problem. Now, again, what's interesting, I live in a little area known as Ranburne, Alabama, or at least that's what's nearby to me. And what's interesting is our declination is almost minimal, which means if you set out to walk north in this area with a compass, north is actually north. They should put that on like the sign. Welcome to Ranburne, where north is almost north. But anyway, don't know what else we'd put on the sign, population 400. But as you move across the United States, you have this declination of your compass, which means, now I'm drawing it rather exaggerated here, but if you actually walked north on your compass, that north is taking you towards magnetic north. And so you have to know how much to adjust your compass by to actually really walk due north geographically. So again, these are things that are kind of being left out and forgotten now because people use GPSs to get where they're going. So again, this was what was known as magnetic declination. We're just reviewing from yesterday. Some interesting little facts about magnets. Normally you do a lab. It's kind of interesting. Jupiter has a very strong magnetic field. We did discuss this yesterday. Magnetic field lines are strongest where the lines are closest together. If you remember, we talked about like where a magnetic field is the strongest. And one of the things I hate the most, I'm going to have to grab a video camera and actually video this because I want you to see it. But the ends of the magnet, the poles are the strongest part of the magnet, but you'll also notice like the greatest concentration of field lines at the poles. Like they'll get a little bit more sparse playing around the middles, but you'll notice this massive concentration of field lines near the end. Magnets are affected by other magnetic fields. If you got, and just out of curiosity, what would happen if you got another magnet and you had like this situation of north and north? It's actually kind of neat what you would actually see like sprinkling the iron. What would happen? North versus north. They repel each other. And what's cool is you would actually see this pattern in like the iron filings if you sprinkled them on the magnet. You would actually see the lines repelling each other from the two magnets. Whereas, let's go over here and for me to doodle just a little bit more. If you had, say, for example, a North Pole and a South Pole, and you could space them out about an inch apart, you would actually see something that looks like this. You would see the field lines then connect between the two magnets. So that's what's actually kind of a neat thing. So you can actually see the attraction just like you can feel it. And one of the other neat things is like magnetic field lines never cross each other. That's why when we draw these pictures, mine's really terrible. Because really, if I was drawing that well, let's look down here. Let's do this time a south-south. If I was just drawing these lines solid, I should take off points for any student that were to draw these and actually have crossing lines on there. These lines will never cross each other. So anyway, that's given us some more magnet basics. All right, so picking up with a guy's name Christian Oersted, he noticed something unique, and this is circa 1820. He found that electric currents generate magnetic fields. I almost wondered in the back of my mind if he was like walking around the lab with a compass and got near an electrical wire and actually saw the compass deflect. And you'll see that if you've got a compass in your house, get near anything pulling electricity and you'll see the compass start to be deflected. Well, if you can deflect a compass with an electrical wire, what does that mean is true about the wire? And we've talked about this before. All a wire is, you can imagine, is it's a carrier of electrons. It's kind of like water flowing through a pipe. You've got electrons in the wire. We call that flow of electrons. We call that current. And so wires have a current. And what's interesting is the current actually flows like in this circular pattern, or not the current, excuse me, the magnetic field, we define that as B in other videos, basically follows like this circular path inside here. Now it's actually, we've got what's known as our right-hand rule number 2. These arrows I've drawn are correct, assuming the current is actually flowing. In my picture, it's flowing up across the page. But we learned a few things. If you can loop this wire together, by looping the wire, you can intensify or strengthen this magnetic field. So a solenoid, which is a highly useful thing, a solenoid is something that we use, and all it is, this is a basic solenoid, and if you look at it, it's nothing more than a coil of wire is all the solenoid is. It's nothing more than a coil of wire. Now I'm going to pull up my little thing. And there's yesterday. So there is our magnet from yesterday with its north and its south pole, and we can see how the compass moves around it. We can also see the electric field around the compass. You can see this electric field. Let's do something. I'm going to try and do something. How about an electromagnet? So an electromagnet, in this case, well, this isn't even it's funny, it's called an electromagnet on this little app I'm using, but this is nothing but a solenoid, is all it is. A solenoid is nothing but a coil of wire, and this is kind of representing electrons moving through the coil. And right now you'll notice there's no electrons moving. And the reason why is I've got no voltage in this circuit. So I'm going to grab this battery and I'm going to bump it to like 3 volts. And instantly you should notice something. You should notice not only the flow of electrons now in this wire, you can see the electrons moving through the wire, but now you should notice, I'm going to grab this compass, a magnetic field. And if you look, I'm going to pass the compass. Literally, can I do it with this app? No, apparently not. I'm going to try and move the compass, though, so literally I can try and get it. Oh, my compass is stuck to the screen. But we can see this compass as it moves around, and we can see this field that's inside here. So if we look at this field closely. This field is the same field as the bar magnet. Look at how the compass behaves. I'm going to move it around, and as I slowly move it, the compass is going to flip directions to show the pole. Let's go back to that solenoid again. And if you really look close, so here we see the south end of the compass pointing into the coil, and as we try to rotate the compass around, look at what happens. It goes to the other end. So the solenoid is nothing but a magnetic field. Now, we can measure that magnetic field. What's interesting, let's get a little meter out here. And let's put that meter like right in front of it. And so overall, we've got 41 Gauss, or 40, let's round it, 42 Gauss in this field. So let's do something. Let's add another coil. And if you notice, it jumped to 55. Well, now let's decrease. Boom. Well, I'm trying to decrease. All the way down to where it's just one coil. And believe it or not, one coil is still a solenoid. All a solenoid is a coil of wire. We hooked it to electricity. So we've noticed that by adding more coils, we were able to strengthen this magnetic field. What happens if I increase voltage? Well, if you take a look, as we increase voltage, we have more current, i.e. Ohm's law. And so we have more electrons, more charge moving, and so we've also increased the strength of our magnetic field as well. What happens to the strength of that field as we get farther away? And you'll notice what's happening to the strength of that field. As we get farther away, we're actually decreasing, the strength of the field is going down. If we went back to a basic bar magnet, let's get a field meter out on it, we'll notice the exact same phenomena taking place. As we get away from the bar magnet, the fields weaken, the fields get farther apart, the lines, and the field weakens. And of course, as we get stronger or closer to the magnet, and we could actually do a lab or something where we were looking at that. Let's go back again to this solenoid. So we've taken a pretty good look at the solenoid. Now this is interesting. We haven't talked about AC electricity yet, but look at what happens when you have an AC electricity source. Look at the electrons in the wire with the AC electricity. If you notice, they're no longer moving in one direction, but what are they doing? They're actually oscillating back and forth and back and forth. And look at what's happening to the magnetic field. The magnetic field, let's get this compass nearby. Watch your compass. Dum, dum. So we can see that this magnetic field is somehow related to the direction of the flow of the electrons. If you reverse the flow of the electrons, you reverse the polarity of the magnetic field. So all that is highly interesting. Now, we use solenoids a lot. We use them, this is actually, this little piece over here, this is your ice maker. What we will do is we actually put like a small magnet inserted into the coil. And what happens is when electricity is applied to that coil, it can actually good grief, where am I from? It can actually pull the magnet into the coil and do something mechanical like open a valve. Sometimes you're sitting by your refrigerator, keep an ear out, and you'll actually hear like a little sound. And what it's doing is opening a valve, and it's letting the water flow to your ice maker tray. And when the tray is full, it turns the electricity off, the valve rebounds back open, and it stops the flow of water. It's pretty ingenious little use of a solenoid. There's also a solenoid mounted to the top of the starter in your car. And so when you actually turn your switch to crank your car, it's actually pulling a plunger down inside of the solenoid on your car, which is actually, and sometimes, have you ever accidentally turned the switch on the car while it was running? Well, when you do that, what happens, it sends this small little gear, and I want to call that Bendix, but I don't know if I'm correct in saying that. But it sends this small gear out against your flywheel, and if the car's already running, you'll hear like a sound because of it. So, anyway, further uses of solenoids. Now, we can take advantage. I'm going to cut this video off in like 1 second. Matter of fact, let's just cut it off now, and we'll pick up next period where they talk about what electromagnets are.